Hello, this podcast is on oscillations and simple harmonic motion. We're going to look at what the difference is between the two. We're going to study key quantities, key relationships, and two specific examples of specific harmonic motion, mass on a spring and pendulums. First, what's the difference? Oscillations, also known as periodic motion, involve repetitive back and forth motion about an equilibrium point. Net force always acts toward the equilibrium point. An example would be a golf ball bouncing up and down on the floor or sine waves. Simple harmonic motion is a special type of oscillation. It has the first two requirements, repetitive back and forth motion about an equilibrium point, and the net force always acts toward the equilibrium point, but it has a special condition. The net force is proportional to the object's displacement from the equilibrium point. So in other words, this net force that's always acting to move the object back to the equilibrium point gets larger the further away from the equilibrium point you get. Some examples here are mass hanging on a spring and a pendulum with small amplitudes, anything less than 30 degrees. Now let's take a look at this golf ball bouncing up and down. It's not simple harmonic motion because the force of gravity is that net force taking the ball to the equilibrium point, which is the floor, and that force is constant. It is not proportional to how far the golf ball is above the floor. Here are examples of the back and forth motion of the mass hanging on the spring and also the pendulum. Let's look at the anatomy of simple harmonic motion. There are key points in the motion. There's the positive turnaround point, the equilibrium point, and the negative turnaround point. And over here we have a table of key quantities. And the first one is the phase constant, and that accounts for where an object is in the cycle. For instance, if it's at the positive turnaround point, this would be the angle at the equilibrium point and at the negative turnaround point. We also have amplitude, and that's how far, that's the maximum distance the object gets from the equilibrium point, and it's represented with A. And then we have our other units here that we're familiar with, and you can see where they reach maximums and where they're zero. A few other terms we want to talk about. Angular frequency, that's the rate at which an object moves through the repetitive cycle. It has units of radians per second. So in other words, a complete cycle is 2 pi radians. So if the object goes through 1 cycle a second, its angular frequency is 2 pi radians. We have our standard frequency, just the number of cycles an object makes in a second. We have our period, that's the amount of time it takes to make one complete cycle. Let's look at some key relationships among the motion quantities. We have our equation for position, and it's a function of the amplitude and the cosine of the position or angle in the cycle. Velocity, of course, is just the derivative of position with respect to time, and acceleration is the second derivative with respect to time of position. This is a helpful thing if you can remember. The acceleration is equal to negative omega squared times x, the position. I will let you know that this equation is on your reference sheet. These others you will have to derive from this or memorize them. Here are the harmonic quantities and the relationships tying period, angular frequency, and frequency to each other. And let's look at our energy quantities. We can see the expression for kinetic energy and the expression for the elastic potential energy. We saw firsthand the motion of the mass hanging on the spring. We don't have that for the pendulum, but this graphic here relates those key turnaround positions and equilibrium positions for a pendulum, and this just summarizes what we covered on the other page as far as our different quantities. And here's the position time graph showing how the phi, the phase constant, changes based on the position. So let's take a look at a problem. The displacement of an object is x equals 8 centimeters times the cosine 2 times t plus pi over 3, where x is measured in centimeters and time is measured in seconds. What is the speed and acceleration at time pi over t seconds? Well, first let's look at the speed, and we know that that's the derivative with respect to time, so we just take our position equation, take the derivative of it, and evaluate it at pi over 2 seconds, and we come up with a speed of 13.9 centimeters per second. For acceleration, we go ahead and take the derivative of the velocity equation with respect to time. We plug in our values and we find out that the acceleration is 16 centimeters per second squared at time equals pi over 2 seconds. Let's look at one more problem. So we have an oscillator and its motion is given by the second derivative of position with respect to time is equal to negative 9x, and it's asking us for the period of oscillation. Well, we know that the period is equal to 2 pi divided by the angular frequency. We also know the acceleration is equal to the negative angular frequency squared times x. We set that equal to 9x. Solve for omega, and once we get omega, we plug that back into our period equation, and we find out that the period is 2/3 pi. Let's take a look at mass on a spring. Specifically, we'll look at the forces. So there's two types of springs. We'll have vertical springs, and here the net force is determined by the gravity force and the spring force. We also have horizontal springs where the mass oscillates horizontally, and here we only have one force, gravity is not part of it, and the net force is equal to the spring force. Regardless of whether we have a horizontal spring or a vertical spring, at the equilibrium point the net force is 0. So notice that for the horizontal spring, that simply means the spring force is 0, so the equilibrium point on a horizontal spring is its natural length, or what we call delta x equals 0. However, when we have a vertical spring, the equilibrium point is not the natural length of the spring because we still have the force of gravity pulling down on the mass and stretching the spring. So the equilibrium point will stretch the spring beyond its natural length by this quantity, mass divided by the spring constant times the gravitational field strength. So let's look at a problem here. A block of unknown mass is attached to a vertical spring of spring constant 5.0 newtons per meter. The equilibrium point is 3/10 of a meter lower than the spring's natural length. What is the block's mass? Well, we just go ahead and take our equation from up here, and we rearrange it to solve for mass, and we find out that the block's mass is 0.153 kilograms. Let's look at the harmonics of a mass on a spring. First, we'll look at angular frequency. We know that acceleration is just the net force divided by mass, and we know that the net force is proportional to the distance the mass is from the equilibrium point. We also know that the acceleration is equal to the angular frequency squared times the position. We can take these two equations and solve them for the angular frequency, and this is the relationship. This is a very important relationship that you want to remember. Also, we can look at the period, and the period is t equals 2 pi times the square root of mass divided by spring constant. You will have this equation on your reference sheet, and then here's that expression rearranged to show you frequency. Let's look at a problem. A 7 kilogram mass is hung from the bottom end of a vertical spring fastened to an overhead beam. The mass is set into vertical oscillations having a period of 2.6 seconds. What is the force constant of the spring? We know our equation here for period. We want to go ahead and rearrange it to solve for the spring constant, plug in our values, and we find out that the spring constant is 40.9 newtons per meter. Here's another problem. A 0.50 kilogram mass attached to a horizontal spring of spring constant 8 newtons per meter vibrates in simple harmonic motion with an amplitude of 0.10 meters. What is the maximum speed and acceleration? At the turnaround point, we know that the net force is at a maximum, and that means that's where we'll find the acceleration at the maximum. So the acceleration is going to be equal to the spring constant times its displacement divided by mass. We plug in our values and we get the answer for the acceleration. At the equilibrium point, we'll find the speed at a maximum, and at this point we know that all the potential energy is transferred to kinetic energy. K times delta x squared is our expression for the potential energy, and we have the coefficient of 1/2 here because half of that was transferred to kinetic. We plug in our numbers and we find out that the amount of energy transferred into the kinetic mechanism is 0.04 Newton meters. We set that equal to 1/2 mass times velocity squared, rearrange and solve for velocity, and we find out 0.4 meters per second is the fastest this mass moves. Let's turn our attention to pendulums. We'll look at three types of pendulums. The first one is a simple pendulum, and this is defined where the string is much longer and lighter than the bob. And when we do that, we can consider the bob a point mass. The driving force, or the restorative force, the force that's always looking to move the bob back to the equilibrium point, is the x component, or the tangential component of the gravity force. Now we're going to derive some of our key harmonic quantities. First, this is the expression for the force, or the tangential component of the gravity force. And of course we know that's equal to mass times acceleration, and we can set that equal to mass times the second derivative of displacement with respect to time. When we're talking about a pendulum, the displacement is the arc. The arc is just the length of the pendulum times this angular displacement. So we just make some substitutions here. And here we're making a very important substitution. We have this expression, negative g divided by L times the sine of theta. For small angles, and that's any angle less than 30 degrees, the sine of theta in radians is equal to the angle in radians. So we can make this substitution here, and that allows us to come up with an expression not based on the arc length, but an expression based on the angular displacement, theta. Notice theta is different. It's a different angle than phi. Phi is the phase constant where we are in the cycle. Theta is this actual angular displacement from the vertical. We take the second derivative of our angular position equation and we wind up with an expression for acceleration, and it's negative omega squared times theta. Notice this is very similar to the expression we had for the mass on a spring, except there we were using x instead of angular displacement. And we also know from up above that our acceleration is equal to negative g divided by L times theta. So we can solve these two equations to get our angular frequency expression and our expression for period. This expression here is on your reference sheet. This is also a very important relationship to understand about pendulums. What affects the frequency or the period is the length of the string and the gravitational field strength. The mass of the bob has nothing to do with it. Let's look at a problem. A simple pendulum has a period of 2.5 seconds. What is its length? Well, we use our equation here for the period of a pendulum. We go ahead and rearrange it to solve for length, and we find out that this pendulum is 1.55 meters long. Now, suppose we took the pendulum up to the moon, where the gravitational field strength is 1.67 meters per second squared. What would the period be? Well, we're using the same equation. We plug in our length, our gravitational field strength, and we find that the period would increase to 6.05 seconds on the moon. Let's look at another problem. A simple pendulum has a mass of 0.250 kilograms and a length of 1 meter. It is displaced through an angle of 15 degrees past the vertical. What is the maximum speed? Well, let's look at some things about pendulums in general. We know this is the position equation. You will find this in your reference sheet. We also know that the amplitude, which is the maximum arc length, is equal to this angular displacement times the length of the string. In this specific case, we can calculate what that amplitude is in meters. Also, we know in general that the angular frequency is the square root of g divided by L. For this specific problem, the angular frequency is 3.13 radians per second. The maximum speed occurs at the equilibrium point, and at the equilibrium point, this expression in the parentheses here is either going to be pi over 2 or 3 pi over 2, depending where you are in the cycle. So we can go ahead and take our position expression, take the derivative of it to get our velocity equation. We plug in our numbers and we find out that the maximum speed is 0.82 meters per second. I happen to pick pi over 2 to use in this problem. That gave us a negative. If we had picked 3 pi over 2, it would have been in the positive direction. But the question asks for speed, which is the magnitude. Next, what is the maximum acceleration? Well, we know the maximum acceleration happens at the turnaround points, and this expression here is either going to be 0 or pi radians. And so we need to get our expression for acceleration. So I took our expression for velocity and took the derivative with respect to time, and that gave us this expression. And of course, when we take the cosine of 0 or the cosine of pi, we're going to get either 1 or negative 1. In this case, I used pi, which gives us negative 1, and the result is we get a positive acceleration of 2.57 meters per second squared. Lastly, what is the maximum restoring force? Well, we don't have to get too complicated with this. We just need to use Newton's second law. Since we know the maximum acceleration, we multiply it by the mass of the bob, and we find out that the maximum restoring force is 0.643 newtons. Moving on to our second type of pendulum, which is a physical pendulum. In this case, the string is not much longer and it's not much lighter than the bob, so we cannot treat the bob as a point mass. Notice that when we have our expressions for angular frequency and for period, the rotational inertia of the pendulum comes into play. This is something you'd have to be given in the problem. You would not calculate it. Also, we no longer have L in the equation, but we have D, and D is the distance from the fixed axis to the pendulum's center of mass. The angular displacement equation stays the same as before, and if we want to convert that into displacement of arc length, the arc length is equal to the length of the pendulum times its angular displacement. Let's move on and look at our third type of pendulum, and this is a torsional pendulum, and this is a rigid body suspended from a twisting wire. So if you think of this wire twisting back and forth and it's rotating, and this causes the rigid body to go through a repetitive oscillation, which happens to be simple harmonic motion. We can see our equilibrium point here and our maximum displacements, which we call the amplitude, represented here. These are our expressions for angular frequency and period. Notice there is a new constant in here, the Greek letter kappa, and that is the torsional constant of the wire. It's something that has to be determined experimentally, and it's similar to the spring constant of a regular spring. Also, we still have L in the equation, but L is the radius of the rigid body. It is not the length of the torsion wire. As before, the angular displacement equation stays the same, and so does the formula for converting angular displacement into arc length displacement. Let's look at uniform circular motion as simple harmonic motion. Here we're taking an object that's going in a circular path, but we're only projecting its motion on the x-axis. So you can see as a result it's going to go back and forth in a repetitive motion on the x-axis. This does qualify as simple harmonic motion because the displacement, of course we know that's equal to x times the radius times cosine theta. But we can write that in terms of our simple harmonic quantities. The displacement is equal to the amplitude times the cosine of the angular frequency times time plus the phase constant. And that's where the amplitude is the radius of the circle and theta is the omega t plus the phase constant. In circular motion, we know the centripetal force is always pointing towards the origin or the center of the circle, and of course that's our equilibrium point in this simple harmonic motion, and it is the x component of the centripetal force that is our restorative force. So our restorative force is equal to the centripetal force times the cosine of theta. We can go ahead and do some rearranging, and we find out that this restorative force is equal to negative the mass times the angular frequency squared. We can take that expression for force and divide it by mass, and we get our expression for acceleration, which is negative omega squared times x. Notice this is the same expression that we got for acceleration of a mass on a spring. Our angular frequency is just the velocity divided by the radius, and our period is 2 pi r divided by the velocity. We could also take the circular motion and project it on the y-axis, and when we do that, here's the expression for displacement, the expression for our restorative force, and the expression for acceleration. Well, that wraps up what we wanted to learn in this podcast, so let's summarize what we've learned. Simple harmonic motion is a specific type of oscillation. There's two requirements. It needs to be a repetitive back and forth motion around an equilibrium point, and its position needs to follow this equation. Second, there's a restorative force that always acts towards the equilibrium point and is proportional to the distance from the equilibrium point. It's this last portion that makes simple harmonic motion a specific type of oscillation. There are key positions, the positive turnaround point, the negative turnaround point, and the equilibrium point, and these have key ramifications on all of our motion quantities as shown here. We also have some key relationships, and it's important to know the expressions for angular frequency based on the type of device and for the period of the oscillation, as well as for the acceleration. So very helpful to get to know these relationships. I hope this podcast gave you a better understanding of oscillations and simple harmonic motion, and have a good day.